Then we have this multi-programming technique where we have understood this through time sharing, where multiple programs are accepted by the operating system, and the operating system will schedule the each program to the processor. Okay, so this particular multi-programming support is supported or is enabled by the operating system by depending on timing functionality. Okay, so the timers could be hardware timers, it could be software timers also. So when I say software timers, it is not like some program is executing continuously to interrupt the processor. The processor itself maintains a timer register. Timer registers mean it's part of special purpose registers where you program the time. Let's say for example I want 10 millisecond uh, time interrupt. So what I do, I convert this 10 milliseconds into CPU equivalent cycles, CPU cycles, and then I will load the value into this register, and the register will continue to reduce by 1 for every clock tick. So it will go one by one, it will reduce. As soon as it becomes 0, CPU itself will interrupt and then it will execute the scheduler. That is one way. Another way is external timer is attached, and there is one interrupt line assigned to this particular external timer. Okay. Any questions? Okay, fine. So this is one small block diagram, or a diagram which indicates how the multi-programming is taken up. So you have multiple jobs. The operating system, this is the main memory. Okay, this is the main memory that we are seeing, where we have the operating system residing in the memory, and it is taking all the jobs simultaneously, and the scheduler is executing on all these jobs. That's the meaning of this particular thing. So what are the advantages that you have with this particular operating system implementation? So you are effectively using the memory. So as long as you have memory, you can take the jobs, right? That's one. The second thing is the throughput is increasing. So that means throughput, when I say throughput, it means how many jobs you can simultaneously give to the operating system and how much time the operating system is taking to complete all these jobs. That's called as throughput. Okay, and the CPU is made sure it is never idle, it is always running. You always burden the CPU. That's what it means to say. Okay. Okay, all right. So this is about the time sharing concept. So where the time sharing or multitasking is a logical extension of multi-programming. So what do you mean by logical extension? So at a time, CPU is executing only one program, but it is giving an illusion. The concept is giving an illusion that CPU is executing multiple programs simultaneously. Okay. So multiple jobs are executed by switching the CPU between them. That means scheduler will do this. The CPU time is shared by different processes. So it is called time shared system. Then we have this time slice is defined by the operating system for sharing the CPU time between processes. So CPU is not involved in what is happening or what it is. CPU will just do what is told. So operating system is telling the CPU to do this. Okay. So some of these examples like we discussed. All right. So we will enter into Linux kernel. Shall I start now only, or? Okay, so I have about 20 minutes. Okay, So we can cover Linux boot, and when we are understanding this, remember how x86 boot worked. Okay, that x86 boot and Linux boot is similar. That means here we will be talking more of Linux specific boot. Okay. Okay, any questions on operating system so far? Okay, cool. Oh, cool. Great. Okay, so let's take up this mm, Linux boot. So, so try to correlate with the diagram that we have with x86, where we were talking about, when x86 is powered on, then the first program that gets executed is the BIOS program or boot program, which will do basic hardware tests, and then it will execute the first stage bootloader or the boot code, which still executes in real mode. And then the bootloader will, since the size of this bootloader is very less, which is 512 bytes, the the responsibility of this bootloader is to load the next stage bootloader, so that the size of this bootloader is not restricted to 512 bytes, but it is restricted to somewhere around one less than 1 mega address locations, or less than 1 megabytes. And the boot, this responsibility of this bootloader, the some of the examples is lilo, grub, etc. This bootloader is responsible to load the given kernel, the next kernel. And so load means reading the kernel, Linux kernel, from the non-volatile memory or hard disk into RAM. So this complete thing is execution. So from here onwards, execution is from RAM. Where does this BIOS program execute from? It executes from ROM, read-only memory, or EEPROM, whatever you call. Okay, and the bootloader grub, for example, it loads the Linux kernel from hard drive into RAM, and then the Linux kernel will execute. So once the Linux kernel has initialized all the operating system resources successfully, it will start executing the user applications. So the first application that Linux kernel executes as soon as its initialization is complete, the first program is called as init. It's called as init process. Okay, so Linux kernel utilizes the processor features. So it divides the processor into kernel mode and user mode. Okay, all the code which is executed or which is implemented inside the kernel is executed in kernel mode of processor, and in beta, sorry, code which is executed inside the kernel, this code actually executes in kernel mode of the processor. Okay, as soon as it is initialized, it will start the first application. The application is called as init application, and this particular init process is executed in user mode of the processor. So let me just write it down. From this part to this part, it is executing in kernel mode. Okay, so after that, all the user programs or the user applications execute in user mode. Okay. Okay, So as soon as the Linux, yeah. So, so the red line that you see here, from this point to this red line, is actually executing in real mode of the processor. Okay. After this, from this point to the applications which are executing, the processor is executing in protected mode. Okay, so the protected mode actually defines two different modes for executing the program into. Okay, one is called as kernel mode and one is called as user mode. Okay, so the kernel mode actually do not have any restrictions on the program that is executing under this. That means the program can access any resources, any resource of the hardware. It can access any memory address, it can access any hardware. Okay, whereas in user mode the program cannot access any resource as such. Okay, so the operating system or the operating system kernel, every time it creates a user, it what it does is it will allocate memory and then it will divide this memory for that program into three sections: text, data, and stack. The text part is read only, data and stack is read write. So this is how it will write, it will allocate memory for this particular user, and the process actually executes in this mode. So what will happen in this mode is the program starts executing, and if it is going beyond this memory boundary, then processor will generate an exception. That's what is the difference between kernel mode and user mode. Is it clear? I'm glad somebody asked about this mode. Is it clear? Okay, so this execution, these modes are talking about program execution. Okay, if you execute a program in kernel mode, there are no restrictions to it. Okay, if you execute a program in user mode, there are restrictions. That's what it means. User space and kernel space, which one? You're talking about this? This user space and kernel space is same as similar to kernel mode and user mode, but these two spaces are defined by Linux kernel. These are the modes. These are the spaces defined by Linux kernel. These are the modes defined by the processor. Uh, um, uh, any questions? Hello. Okay, so as soon as the bootloader loads the kernel into the RAM, the structure of the RAM will look like this. This is the zero address, this is continuous. This is as soon as and when you go up, the address size increases. This is the so the data, the structure of memory that you are seeing here is actually defined by Linux kernel. So Linux kernel will define how the program or the operating system has to be copied into RAM. Okay, so as soon as you power on, the BIOS program will be can be accessed from these address locations. So these are the address locations where the ROM is located from 0 to 6. These are all in hexadecimal, 600 hex. Okay, so now as soon as the BIOS is executed, the BIOS will load the first stage bootloader at this location. Okay, so once the BIOS is executed, the first stage 512 byte bootloader is executed, it will copy the next stage bootloader at this location. So this, up till this point, it is a common for any operating system that you are trying. This is processor, this is up till the boot sequence, up till the bootloader sequence, that is up till this stage. Is it clear? The next stage is depends on the operating system that is loaded. As per the Linux kernel expects the kernel code to be loaded at a specific location. Let's say you load the kernel at X address location, then at the address location X plus 8000 hex, it expects some stack to be allocated, so the bootloader will load the kernel at X address, and then it will start executing this particular kernel. Okay, now the kernel setup, what it does is, before even executing any other piece of code, it has to initialize the stack. Why does it need stack or heap? Stack is required for function calls. Linux kernel is implemented in C language, so C language supports function calls, and function calls are implemented by using the stack. Remember the previous classes where we understood how the function calls are implemented. So as soon as a function is entered, a push operation is done. As soon as the function is completed, a pop operation is done. So push and pop operation happens in stack. And why do you need heap? If a kernel code allocates memory dynamically, then those memory addresses are stored in heap, so that Linux kernel can monitor what are all the dynamic or the memory that is allocated to the given kernel code, and whether it is properly utilizing that particular memory or not. Okay, so first it will do the stack or heap initialization, of this much size. So if you subtract 10,000 hex with 8,000 hex, you will end up having 2,000 hex. That is the initial size of stack or heap which is allocated. You see on the right side, it is showing the mode in which the kernel starts executing. So up till this point, the kernel setup is done, kernel boot code is completed, these two have initialized the stack or heap. Kernel can take certain command line parameters from the bootloader, so it can do those bootloader command line configurations, and the command line has to be copied by the bootloader at the location X plus 10,000. Okay, after the command lines are initialized, read properly, it will react to those command line parameters. Then it will move the processor from real mode to protected mode. As soon as the code is moved from real mode to protected mode, it will jump to this address location 1 2 3 4 5 6 100,000 hex value. It will jump because the protected mode code is available from this location, and then this code is executed. This is too much. I think so many questions are coming. So let me tell you that this is the protocol of Linux kernel. This is the entire protocol of Linux kernel which bootloader has to follow so that Linux kernel can boot properly. Yes. Uh-huh. Okay. Okay. Yes, this is for Linux OS. So right from this X onwards, from X onwards, this is for Linux OS. Below X is a common memory structure independent of whatever is operating system that is going to be run. So even if it is Windows, if it will be after X, this X is also defined by Windows. The complete protocol is also defined by Windows. Is it clear? Is my statement clear? So grub is here. So grub is capable of booting Linux kernel. It is capable of booting Windows also. So grub understands the protocol of Linux kernel. Grub understands the protocol of Windows also. So when the x86 is powered on, as soon as you stop the bootloader, you will see the memory map like this in this format. Okay. So yes. Normally, we will have two stage. More than two stage, it doesn't have, because as soon as you power on, this BIOS executes. This is also called as boot code, right? Because it is executing during boot. So this is normally zero stage. This bootloader is divided into two stage. This is stage one. This is stage two. And if you go through grub, right, grub documentation, they divide the bootloader into three stages. They call it, this is stage one. They divide this bootloader into two more stages. They call it 1.5 stage, stage two. So there are three: stage one, stage 1.5, stage two. Yeah, yeah, we can see. Yeah, yeah. Grub has very good documentation. We can see what is happening. I can share those links if you need. I can share it in this presentation itself. Maybe at the end of the presentation, I can add those things, because yesterday also we were discussing about content for understanding operating systems, computer architecture. So we can put all this in one slide and share. When I mean, if you want to learn something, you have to, you need to work hard. So you need to learn. What I'm telling is not even 5% of of what is actually happening, right? If we have to tell everything, then it won't be an institute. No, it won't no more be an institute. It will become like a college or something. So I would like to stop here, and because the next slides onwards is more of Linux kernel specific, and maybe in next class we will go into Linux kernel closely. Okay, so the requirements I have sent it to Vignesh, and Vignesh is aware. I think he can tell you. She is also aware. Yes, 7 a.m. How many will be coming? 7 a.m. Uh, oh wow. Yes, I can make on Tuesday. Yes. Okay. Yes. I remember Subhashini came only once or twice when I took 7 a.m. class for them. Okay, sure, sure, no problem. It's not it's not a force. I'm just trying to see if I can spend some time, and for me, weekdays 7 a.m. will be a good time so that I can go to office and I can also take care of handling the class. So Rajinish is also coming.